Hello, my name is Barak, Davidi, and this summer I worked with the Dang Energy and Nanotechnology Group on a literature review of flame-synthesized nanomaterials for biomedical applications. Nanomaterials exhibit different physical and chemical properties in the nanoscale compared to their bulk form. As such, they are utilized in a range of science and engineering fields, but the focus of this review was their biomedical applications. The methods of synthesizing nanomaterials can be categorized as top-down or bottom-up approaches. Top-down approaches, which require the expenditure of energy to reduce particle size down to the nanoscale, differ from bottom-up approaches, which build particles up to the nanoscale. In vapor-fed aerosol flame synthesis, volatile precursors are combusted. Particles are formed after precursor conversion by nucleation from the gas phase and grow by surface reaction, coagulation, and subsequent coalescence into larger particles which deposit on the substrate. The advantages of flame synthesis are process speed, on the order of kilogram per hour, not milligram per hour, which is typical in some wet chemistry techniques, cost effectiveness, and the possibility of scaling up to industrial scales. Furthermore, this technique can offer greater synthesis control over traditional methods. The research project aims to incorporate flame synthesis for biomedical applications. The goals are to propose a methodology to synthesize existing and novel nanomaterials with greater scalability, process speed, and cost effectiveness. This diagram summarizes my process. I read and annotated articles, examined the methods section, and considered adaptations for flame synthesis. I attempted to form one interesting idea into a workable proposal and presented these ideas to my lab. I incorporated their feedback and searched for new articles. The results are comprised of a series of workable proposals for MIT Dang. The topics are listed here and will be discussed in details for the remainder of the presentation. The research question was, can we increase the filtration efficiency of cloth face coverings in the 100 nanometer particle size range by adding electrostatic filtration and material coating utilizing flame synthesis? This is especially relevant since COVID-19 is about bioaerosol with a mean particle size of 100 nanometers. On the right, first four mechanisms utilize mechanical filtration, and the last predominates the removal of low mass particles where a dipole is induced in the neutrally charged aerosol and results in attraction to the negatively charged fiber. Creating materials that are suitable for this process can be achieved by directly depositing self-assembled metallic nanoparticle arrays on a mechanical filtration layer, such as a cloth face mask. There are several options for charging these metallic layers, such as nanogenerators, which leverage the frictional force of breathing, temperature gradients or pressures, external batteries, or passive methods, such as redox reaction in the presence of humidity. The next research question was, can we improve the sensitivity, lower limit of detection, and selectivity of chemoresistive breath sensors by utilizing flame synthesis and sensing films? Human breath sensors must have sufficient sensitivity and lower limit of detection to detect breath markers accurately at trace level concentrations. Flame synthesis offers the advantage of flame homogeneity, for the sensing film can be deposited directly on the electrode. Additionally, higher porosity can be achieved, which facilitates gas transport and enhances resistance modulation. In the figure in the middle, an ammonia sensor was developed with 5 parts per billion lower limit of detection. The human breath sensor must also have highest selectivity to accurately detect single breath markers against other compounds. In the diagram on the right, molecular sieves can be utilized to increase selectivity of metal oxide sensor arrays. Flame synthesis offers the possibility of implementing breath sensors on non-traditional substrates, such as smartphone cases and toxic gas sensors on emergency medical responders' clothing. The final question was, can we create wound dressings that exhibit selective antibacterial properties triggered by the immune response? The use of antimicrobial serval has been growing over the past decade. With many of these applications, lack is selective release of the antibacterial silver cation. Colloidal electrospinning enables control of the nanoconfinement conditions of the active agent in non-woven polymer meshes that can be employed as wound dressings. One potential method of modulating this cytotoxicity is by coupling the silver with gold, which serves as an electron source and prevents the oxidation of silver. In the presence of reactive oxidizing species, which are produced by the body's immune response, the silver is oxidized to silver cation and becomes cytotoxic. This can be achieved by creating wound dressings with metallically porous thin films or by coaxial electrospinning of these nanomaterials. The review is ongoing, and proposals may define new research directions for the Dang Energy and Nanotechnology Group. I would like to acknowledge my PI, Dr. Dang, and my graduate mentor, Manasa, as well as the MSRP program coordinators. Thank you.